All right. Hello, everyone. So I'm just going to be talking to the students mostly. I just want to say congratulations to everyone who participated. And I also want to say if you think that you might have struggled on this, that's good. The struggle is good. And I think they did a good job making an interesting test this year. And so if you felt like it was hard, this is a great opportunity to get better. As long as you focus on trying to not make the same mistakes in the future, then you're on the right path and you'll be doing great. Um, so let's go through this. I do want to solicit some volunteers, but I'm going to try to go through these. And I don't know who answered what. I do want to shout out one of my students for doing very well. They got a very high score, and I'm really proud of them. I don't think they're here, but uh, anyway, so um, problem one. The eight-pointed star shown in the figure below is a popular quilting pattern. What percent of the 4x4 grid is covered by the star? So, one of the easiest ways to solve area problems is to chop up the shape and rearrange it. So, I'm gonna chop off these two triangles here, these two here, and I'm gonna slide them over here. Okay. And we get a new shape of a shaded region, which is a 2x4 rectangle, which is half of a 4x4 square. All right. So the table below shows the ancient Egyptian hieroglyphs that were used to represent different numbers. And we have these symbols here. For example, the number 32 was represented by cap, 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 line, line. What number was represented by the following combination of hieroglyphs? Stick, swirl, 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 cap, cap, line, line, line. So we have a 10,000 plus a 400 plus a 20 plus a 3. That looks like B to me. All right. Feel free to like raise your hand or put a question in the chat if you want to talk about this current question, and I'll slow down. So Buffalo
Mr.
Shuffalo.
Gorman, can you maybe zoom in the PDF a little bit more? That'll help. Thank you.
Yes, sir. All right. So Buffalo Shuffalo is a card game in which all of the cards are distributed evenly among all the players at the start of the game. When Annika and three of her friends play Buffalo Shuffalo, each player is dealt 15 cards. Suppose two more friends join the next game. How many cards will be dealt to each player? All right, so we need to figure out how many cards are in play. We have four people, and they each get 15 cards. That is a total of 60 cards. If we have four people and we add two, then we have six people. We need to divide 60 by two, and that gives us 10. So 10 cards will be dealt to each player. Lucas is counting backwards by sevens. His first three numbers are 193 and 86. What is his 10th number? So um, let's first write down the numbers that he's going to say backwards, at least the first one and the last one. So, or what he's subtracting by. So first he subtracts 0, then he subtracts 7, then he subtracts 14. The last one that he subtracts is actually going to be 7 times 9. The reason it's 7 times 9 is we started counting at 0. This is something that's common when you're dealing with this kind of pattern. You have to be careful about when you start counting from 0. So 100 minus 63 is equal to 37, which is B. All right. Betty drives a truck to deliver packages in a neighborhood whose street map is shown below. Betty starts at the factory, labeled F, and drives to a location A. Okay, so she goes here, and then here, and then here, and then here. But she doesn't just drive straight through buildings, she follows the streets. So what's the shortest distance in blocks she can drive to complete the route? Um, all right, so Zoom gave me a notification. So what we can do is we can go like this, like this, like this, and then like this, like this, like this, like this. So this first one is 3, second one is 10, and then this is 6, and this is 5. And when we add that all up, we get 24, which is C. All right, so Seku writes the numbers 15, 16, 17, 18, and 19. After he erases one of the numbers, the sum of the remaining four numbers is a multiple of 4. Which number did he erase? So, whenever I see something like is a multiple of 4, um, I know that I'm allowed to save a ton of work. This is something that I usually spend a little bit more time talking about in my class, so forgive me if I'm going a little fast. But whenever we're talking about multiples of numbers and adding them up to get multiples of other numbers, we're really talking about a number circle. So here we have the usual number line. We're going to write out a few examples of it. 6, 7, 8, and then maybe just a -1 and then a -2. And then when we're talking about multiples of numbers and their remainders, it's kind of like we take this circular stamp wheel, right? It's got a 0 on it, it's got a 1 on it, it's got a 2 on it, and a 3. And then we roll it along the number line back and forth, and we stamp the number line with a new set of labels. So this becomes 0, 1, 2, 3, 0, 1, 2, 3, 0, and then backwards as well. Okay, so why would we do this? Why is this helpful? It allows us to save a bunch of brain power from doing arithmetic. So 15, its remainder when we divide by 4 is 3. 16, its remainder when we divide by 4 is 0. 17, its remainder is going to be 1. This is going to get labeled with a 2, and this is going to get labeled with a 3 again. And when we add these up, what we see is we get 9. So um, after he erases one of the numbers, the sum of the remaining numbers, the four numbers, is a multiple of 4. Oh, I got a question. Yes, the diagram is related to modulo. Thank you, someone, for bringing up that word. So what we're doing here, when we relabel the number line, is called modular arithmetic, just some vocab. But doing this is usually really helpful. We don't care that much about the specific information, how big 15, 16, 17, 18, and 19 are. We only care about what the remainders are after we divide by 4. So um, we get 9. We have to erase one of these numbers and turn it into a multiple of 4. Our only option is to erase 1, which corresponds to 17. So on the most recent exam in Professor Zochi's class, 5 students earned a score of at least 95%. 13 students earned a score of at least 90%. 27 students earned a score of at least 85%. And 50 students earned a score of at least 80%. So how many students earned a score of at least 80% but less than 90%? Well, I just like to draw on top of my tests. It makes it easier for me to think. We can see that pretty much everyone, all 50 of them, got at least an 80%. But how many got less than a 90%? Less than a 90% is down here. We have 13 above and 50 down here. So that means we have to have 50 minus 13 in here. That gives us 37. Can't you just average out the numbers in question 6? It does work out that way, but I would be interested in your logic about why it would work. What would the average where we're dividing by 5 tell us about being a multiple of 4? It's a good observation, but you would have to make a logical argument. Yes, the average would be 17. That's a correct observation. It's just not necessarily always the correct strategy. Um, any other questions before I move on? I feel like I'm going kind of fast. No questions? Okay. All right, so Isaiah cuts open a cardboard cube along some of the edges to form the flat shape shown on the right, which has an area of 18 square centimeters. What was the volume of the cube in cubic centimeters? So let's call this S for surface area of the face. We have 6 faces, so 6s um, equals 18. All right, and that means that s is equal to 3. That means that the side length of one of these squares is the square root of 3. So this is square root of 3, this is square root of 3, this is square root of 3. And the volume of a cube is just what we get when we multiply all its side lengths together, which would give us a, 3 times the square root of 3. All right, so Ningli looks at the 6 pairs of numbers directly across from each other on a clock. She takes the average of each pair of numbers. What is the average of the resulting 6 numbers? This one is kind of cool. Um, I am going to maybe not do this the brute force way and use a little bit more algebra than you might need, but it'll be because we're going to see some cool tricks. So I'm just going to write this out. We're adding up 1 plus 7 over 2. That's the average of that. 2 plus 8 over 2. All right, and then all the way down to 6 plus 12 over 2. And then we're taking the average of all 6 of these. Okay, this looks like a really ugly expression that they're asking us to compute. But if we're clever, we can simplify it. And I'm going to start by making it all under make it be all under one fraction bar. So we can pull a 1/2 out of all of these. So we have 1/2 times 1 plus 7 plus 2 plus 8 plus all the way to 6 plus 12. So if we simplify this even more, we have a 12 here, and then we have all these numbers written in order. 1 plus 2 plus 3 plus 12. Okay, so if you've had my class before, at this point you might be saying, "Oh, I know how to add up a list of consecutive numbers." Gauss taught us how to. It's really easy. We just do we say that our sum is s, and we do 1 plus 2 plus all the way down to 12, and then s is 1 plus or 12 plus 11 plus all the way down to 1. Add these up. 2s is equal to 13 plus 13 plus 13, or 2s is equal to 12 times 13. So then s would be 12 times 13 over 2, which is 6 times 13, which is 78. Okay, so we could just say this is 78 over 12, which would give us 9.5, which is D. However, that's not the right answer. Am I making a mistake here? Yes, I know what the mistake I'm making is. 78 over 12 is 6.5, not 9.5, 6.5. There's 6 12s, and then 78 minus 72 is 6, which is half of 12. Okay, but there is a faster way even. According to Gauss, actually, we are looking for the average of the sum of this number. So let me just erase all this work. We're looking for the average of this. We have 12 times 13 over 2 over 12, which is just equal to 13 over 2. That might have been simpler than what I was doing. Yeah, yes, that's Gauss's formula. Thank you for pointing that out. What this formula tells us is that if we want to find the average of the first n consecutive numbers, I'll say n now. So we got 13 over 2, but in reality, if we have 1 plus 2 plus all the way down to n, that is, according to Gauss, n times n plus 1 over 2. But if we want the average of these numbers, according to Gauss, that should be n plus 1 over 2. So if you actually just remember this formula the next time you see a question like this, you could save yourself a ton of work. You could just say, oh, 12 plus 1 over 2, which is 6.5. All right. This next one is pretty good. I think they did a really good job on some of the questions this year, and the next few are some of my favorite on this test. So in the figure below, ABCD is a rectangle with sides of length AB equals 5 inches and AD equals 3 inches. Rectangle ABCD is rotated 90 degrees clockwise around the midpoint of side DC to give a second rectangle. What is the total area in square inches covered by the two overlapping rectangles? Okay, so we want to find the area of this square. If we can find the area of this square, then let's call it little a, and let's call the area of the big rectangle capital A, which is 3 times 5. Then we can just do big A plus big A minus little a is equal to the overlapping area, the total. Okay, so um, we have 15 plus 15 minus the little a is equal to the total. How do we find what little a is? The key point comes from the use of this word midpoint. Midpoint means it's half of 5. So this is 2.5 right here, this side length. And so the area is of this square is going to be 2.5 squared. So we have 30 minus 2.5 squared, which is equal to 30 minus, I just happen to know off the top of my head that this is 6.25. I'm going to trust that you guys know how to do long multiplication. And so we get 23.75, which is D. All right, we're making pretty good time. So a tetromino consists of 4 squares connected along their edges. There are 5 possible tetromino shapes, I, O, L, T, and S, shown below, which can be rotated or flipped over. 3 tetrominos are used to completely cover a 3 by 4 rectangle. At least one of the tiles is an S tile. What are the other 2 tiles? Okay, so, well, how many ways can we cover the square? In 10, how do you know that the overlap is a square? All right, great question. So what we do know, sorry, everyone, I know I just read out question 11, but I got a question about question 10, so I'm going to go back to that. What we do know is that if we flip this over like this, then it's going to land back on itself. And what that means is that this is perpendicular. Okay, so um, we know that we have a quadrilateral whose diagonals are perpendicular. That doesn't necessarily make it a rhombus or a rect. Oh, I have another question. Can it wait until I've answered this question? Is that all right, Joshua? Thank you, sir. Um, so we have a quadrilateral whose diagonals are perpendicular, and we know this is 2.5. And after we rotate this, it doesn't change lengths, so we know that this is also 2.5. But now what we have is an isosceles triangle, and we know that these are perpendicular, so its height is perpendicular here like this. I guess we already knew that. Um, but oh, it's isosceles, so this has to be 45, and this has to be 45, and so then it's a square from that, and we can also then reflect it over this line. Let's do it in blue. If we reflect it again, then we get this is also 45 and 45 and 90. So I would just use symmetry. You don't have to do this much work, but someone was interested in proving that exact step. Um, if you have reason to believe it's some other shape, then I might be interested in hearing that, but otherwise, uh, it's just practice. All of you guys can know all this stuff if you just practice. I promise it's all possible in less than 10 years. So, I'm going to reread problem 11 and then solve it. So now 1 year is a ton of time. You can do all of the past tests in less than 1 year. Can you go over the first 9 questions at the end of class? Yeah, I don't mind repeating myself. We have a lot of time available, so I'll skip back to the beginning. So A tetromino consists of four squares connected along their edges. There are five possible tetromino shapes, I, O, L, T, and S, as shown below, which can be rotated or flipped over. Three tetrominos are used to completely cover a 3x4 rectangle. At least one of the tiles is an S tile. What are the other two tiles? So, let's first talk about how we cannot put the S tile in here. If we put the S tile like this, that's bad. We can't do that. So let's ignore that case. Otherwise, we could put an S tile like this. Okay, and let's just try out these options. Let's just see if we can fit it in. If we try to put an I in, that's not going to work. Okay, so because it'll create this pocket right here. Sorry if I went too fast. This little pocket means we won't be able to fill it in. So that's not going to work. Any answer with I in it, we can just cross out. All right. So we have L and L, L and S, or O and T. Let's just try an L. Okay, so we can put an L here. And we can put an L here. And that works. So we could do C. In fact, the answer is C. Um, you could put the S in a bunch of different ways. Um, so, for instance, you could have it like this. But that's kind of just a reflection of this one. And we're going to have two L's in that one also. Um, we could also, if we felt like it, put it in like this. That would work out. But again, that's just kind of a double reflection of the first case. So there's one other way we could put it in, but actually this one won't work anyway. We could put it in like this, and it wouldn't be a reflection of anything we've talked about. It just also wouldn't work. So the only cases that are possible, we require two L's. You can also check that these wouldn't work. You can put it straight up in the middle. How can you annotate what you mean? What do you mean straight up in the middle? Like this? Oh, I know I see. Yeah, there you go. Sorry, like that. That's right, Terry. And then we could have an L here and an L here. That would also work. All right, so the region below consists of 24 unit squares, each with a side length 1 centimeter. What is the area in square centimeters of the largest circle that can fit inside the region, possibly touching the boundaries? All right, so the largest circle we can draw inside of this thing, it passes through these points. It's going to have to touch some of the corners, and it passes through these 8 points. These 8 points are one down and two left or right, or one up down, two up downs, and one left or right away from the center. So according to the Pythagorean theorem, this is the square root of 5. Okay, so radius is equal to square root of 5. According to Archimedes, the area is r squared pi. So that is 5 pi, which is C. All right, so each of the even numbers 2, 4, 6, dot, 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 all the way to 50 is divided by 7. The remainders are recorded. Which histogram displays the number of times the remainder occurs? So this is another example where we're looking at a number wheel. And that's helpful for later, but I'm just going to write down what we get. So 2 divided by 7 has a remainder of 2, 4 divided by 7 that has a remainder of 4, 6 divided by 7 that has a remainder of 6, 8 divided by 7 that has a remainder of 1, 10 divided by 7 that has a remainder of 3, and then 12 divided by 7 that has a remainder of 5, and then 14 divided by 7, that's actually just a multiple of 7, we get 0. And then we're going to notice something. 16 divided by 7 that has a remainder of 2, 18 divided by 7 that has a remainder of 4, 20 divided by 7 that has a remainder of 6, 22 divided by 7, that has... Oh, um, sorry, I got a question about the previous one. Um, so apologies, I'm going to scroll back up. Um, so Archimedes told us that the area is the radius squared times pi. And then the other thing that Archimedes told us is that the circumference is equal to 2r pi. So 2r pi, 2 root 5 times pi is equal to the circumference. 2 pi r squared with a radius of 2. Uh, I don't think so, because that would be for a slightly smaller circle. If the radius is 2, then it would uh not be big. We could make it bigger and it would still fit inside the shape. Sorry, I misunderstood the question the first time. Um, oh, a few people think it's 2. So let's zoom in real close. Okay, so this shape is symmetric, so the center of the largest circle is going to be at the center. This right here is 2, right? So this is 2, this is 2, this is 2. But this circle doesn't even touch the outside of this shape. Um, Maybe I could draw that a little bit better. But it never touches any of the corners. If this was a balloon, then we could keep blowing more air into this thing. And actually, the one that we want just goes slightly outside of 2. Slightly longer than 2. But it does go through all of these corners. So it goes out here. That is 1 this way and 2 this way. So I'm just going to remind everyone of the Pythagorean theorem. This theorem is actually much older than Pythagoras, and they call it different things in different languages. But in English, um, the Pythagorean theorem says that whenever we have a right triangle, that's the same thing as saying that a squared plus b squared is equal to c squared. The square of the two side lengths is equal to the square of the hypotenuse. So we could use that information here to find the radius of the largest circle. So let's call this c, then 1 squared plus 2 squared is equal to c squared. So c is equal to the square root of 1 plus 4, which is equal to the square root of 5. Yeah, this one's really sneaky. This one's really sneaky. Okay. I'm gonna start waiting longer between answering, or yeah, to give people time to ask questions. So, um, if you have a question, but it might take more than like 5 seconds to type, then just raise your hand, and then I'll wait for you to type it if you don't want to speak. Um, but I'll give you time to type it out. So, let me reread this question and remind you of our strategy. Each of the even numbers 2, 4, 6, all the way up to 50 is divided by 7. The remainders are recorded. Which histogram displays the number of times each remainder occurs? Okay, so I just started brute forcing this. I guess I'll write beneath it what we had here: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So, someone who doesn't think that they got this correct, is anyone seeing a pattern here? Can anyone describe what's going on here with their own words? Go ahead, Joshua.
So I mean like I don't really see a pattern, but what I did was actually just use the like I just use elimination.
Oh, no, I'm asking if you see a pattern. Does anyone else see a pattern?
Um,
Go ahead,
Morning.
Davis.
So the black numbered numbers are the remainder divided by 7 by the red colors.
Yes. What's happening to the black numbers?
So the black numbers um are the remainders of like the red colors. And
Yes. Is there something suspicious happening after the 0?
it's repeating.
It's repeating. Okay, so this is 7 long, and we have 25 numbers. So this repeats 3 times, and we have 4 left. Okay, so those are going to be 44, 46, 48, and 50. And it's going to be 2, 4, 8, and sorry, 6 and 1. So I think that should come out to A. Yeah. So we have a baseline of 3, but these 4 get 1 extra 1. This one is question 13. Any questions before I move on? I'm taking that as a no. So a number n is inserted into the list 2, 6, 7, 7, 8. The mean is now twice as great as the median. What is n? So when they say the median, that's hint that there's exactly 1. So the median doesn't change. In this case, the median is 7. So the mean is now 2 times 7. So we have 2 plus 6 plus 7 plus 7 plus 28 plus some number n, all divided by 6, because we're taking the average. That's equal to 14. So if we multiply 2 plus 6 plus 7 plus 7, or sorry, not multiply, add. So we get 8 plus 7 is 15 plus 7 is 22. 22 plus 28 is 50. And then, so we have 50 plus n is equal to 84. Oh, did I do my math wrong? Let's see. 8 plus 14 is 22. That's 50. 6 times 14, that's 84. Oh, n equals 34. Sorry. I doubted myself, but I got it right. So that is E. Is there a whiteboard or anything that we can look at, or are we just listening? I am sharing my screen, but one person is telling me that they are having difficulty seeing my screen. Um, oh, good question. So someone is asking, what does mean and median mean?
Well, I
Before,
heard
wait,
I heard that it's just
pardon,
like a
I'm not asking for feedback. Uh, so one thing I would like to say is please be nice to each other in chat. Please be gentle to each other. We're all here just to learn math. No need to start any fights in the chat. So there's 3 vocab words that I would like to talk about here. Um, so the 3 vocab words are mean, median, and mode. And these are from statistics. So statistics is when we have a lot of information and we want to summarize it with a single number. So the mean of some numbers, like this list right here, is the average. So here we took the average. This is the same as the mean. The median is the middle number. Right now the middle number is 7, and then when we have 6 numbers, the middle number is going to be the average of these two. But 7 plus 7 over 2 is just 7 again. So the median is the middle number, and then the mode is the number that appears the most. So median is kind of like middle, and mode is kind of like most, as just on the level of being words, but they also have the same meaning when they're describing mathematical operations. So we get 34 for this one. All right. Stay with me for 5 more minutes. I know that an hour and a half is a long time to sit down, so I usually like to give a 5-minute break in the middle of a 90-minute lesson. Did we skip question 13? I don't think we did. So give me 5 more minutes of focus, and then I promise I'll let you guys get up and stretch. So problem 15. Kai draws a 6x6 grid. He colors 13 of the unit squares silver and the remaining unit squares gold. Kai then folds the grid in half vertically, forming pairs of overlapping unit squares. Let lowercase m and capital M equal the least and greatest possible number of gold on gold pairs, respectively. What is the value of m plus n? So M is going to occur when we have the least amount of gold on gold pairs. So let's take all 13 silver squares and place them like this. So that the silver ones are outside of the gold. So this is the gold one, and then the silver ones are the others. Sorry. So this is the gold. From this, we can see that we're only going to get these being paired up. So lowercase m is equal to 5 pairs. All right. And now what is uppercase M going to be? Uppercase M occurs when there's as many silver pairs as possible. So let's put the gold pairs like this. Oh, oops, I drew it wrong. Let's put the gold like this. Okay, so we have 6 silver over here and 7 silver over here. Then all of the stuff that is going to work is going to be these pairs. And we can see 11 of those for a total of 16.
Yeah.
All right, so 5 distinct integers from 1 to 10 are chosen, and 5 distinct integers from 11 to 20 are chosen. No two numbers differ exactly by 10. What is the sum of the 10 chosen numbers? Oh, sorry. Does anyone have questions about 15 before I answer 16? I don't see any questions, but I just immediately went to the next one. So, okay, so we chose 5 numbers from 1 to 10 and 5 numbers from 11 to 20, and none of them, if we take the difference, is 10. What is the sum of the 10 chosen numbers? In a question like this, sometimes for like questions 16 to 20 on this test, you can be like really smart and come up with a whole bunch of ideas about this, or you can just try to write it down. So I'm going to make the first 5 numbers as small as possible, and the next 5 numbers as large as possible, so that there's no way any of them are divisible by 10 or have a difference of 10. So we're just going to do 1, 2, 3, 4, 5, and 16, 17, 18, 19, and 20. Okay, so what happens if we add each of these up? I'm going to do it backwards like this. We get 5 times 21, which is C, 105. Angela, can you check for me and see what the sum is when you do that one? So, I guess other people can check this too. Our friend Angela has suggested that we do 1, 3, 5, 7, 9, and 12, 14, 16, 18, and 20. Angela was thinking, yes, we can go over 13 later. Angela was thinking, okay, what if instead of making them as small as possible, as big as possible, so that none of them have a difference of 10, what if I just make the first 5 odd and the second 5 even? Angela thinks it's also 105. We can actually see that it's 105 just by pairing them up in the same way. It's also equal to 5 times 21. So, this problem is really cool because there's multiple ways of doing it. All right. Yeah, I think this test was really interesting. And, I mean, in particular, question 17 is related to something that I study a lot in my master's degree. So, in the land of Markovia, there are 3 cities, A, B, and C. There are 100 people who live in A, 120 who live in B, and 160 who live in C. Everyone works in one of the 3 cities, and a person may work in the same city where they live. In the figure below, an arrow pointing from one city to another is labeled with the fraction of people living in the first city who work in the second city. For example, 1/4 of the people who live in A work in B. How many people work in A? All right, before we solve this question, I just want to give one piece of vocab. A diagram like this is called a Markov chain. Okay. You probably will not hear that word unless you study math in college again. You probably won't hear it again unless you study it in college, but that's why they called this Markovia. Markov chains are very important and they pop up in a lot of different places. So, let's write the number of people who live in each town right here. That'll help us out. So, the people leaving A each day is 1 minus, the people who stay in A each day is 1 minus 1/4 minus 1/5 times 100. And the people who are entering A each day is 1/3 of 120 and 1/8 of 160. Okay, so let's figure this out. 1/8 of 160 is 20. 1/3 of 120 is 40. Okay, now we have 1 minus 1/4, that's 3/4, minus 1/5 of 100. There's a couple different ways that you can do this. You can either combine the fractions and then figure it out, or you can distribute the 100. I'm going to distribute the 100 because it's easier for me to work with whole numbers than fractions. So we have 20 plus 40 plus 75 minus 20. So this cancels with this. 40 plus 75 is D. 115 people work in A. All right. So any questions about this one before I move on? Uh, uh, so yeah, David, you're asking really good questions, but they're not strictly necessary in order to get the right answer, and we have a limited time available to us. So maybe in the future I can talk to you about that question more, but I think you should just hold on to that question and investigate it yourself because it's a good question. All right, so the circle shown below on the left has a radius of 1 unit. The region between the circle and the inscribed square is shaded. In the circle shown on the right, 1/4 of the region between the circle and the inscribed square is shaded. The shaded regions in the 2 circles have the same area. What is the radius r in units of the circle on the right? Okay, so if you take my AMC8 class, you might know that the area of a square is half of the product of its diagonals. So This has a diagonal length of 2. This has a diagonal length of 2. So the area of this square is 2 times 2 over 2, which is equal to 2. Using the formula that Archimedes told us, when the radius is 2, the radius is 1, then the area is just pi. So the smaller shaded region, or I guess the shaded region on the left, is pi minus 2. That's also what's going on over here, except we're going to take a quarter of that. So we have the area of this square is 2r squared over 2, being subtracted from the area of the circle, which is r squared pi, and then we're dividing that by 4. Are there a lot of different ways to solve question 17? There are definitely a few different ways to solve this. I took a whole college class on how to solve problems like this. You could spend your whole life talking about questions like this and different ways of solving them. So I don't know if that answers your question, but yeah. So why is the area 2? Okay, so if you have any square, and let's say we know the length of the diagonal, right? So this is D, this is S, this is S. Okay, on one hand, we could just say that the area is S squared. But D is actually related to S. According to the Pythagorean theorem, D is S times the square root of 2. So if we did D times D, that's equal to 2S squared. So S squared is equal to D squared over 2. Since this diagonal is 2, then we get that the area is 2. That's one way of getting the formula. There are other ways, but they involve me yapping for more than 15 seconds. So that's what the class is for. That's why we go over the specific topics. All right, so we have pi minus 2 is equal to this ugly thing, r squared pi minus, this becomes 4r squared over 2 over 4. So this cancels with this to become a 2, and I'm going to multiply both sides by 4. So we get 4 pi minus 8 is equal to r squared pi minus 2r squared. If we pulled the r squared out, then I shouldn't have multiplied that 4 in. We just have, and this is getting messy now. Sorry, I'm writing it not sequentially. So we have 4 times pi minus 2 is equal to r squared times pi minus 2, just by factoring out the r squareds here. And we can just cancel out the pi minus 2 from both sides to get r squared is equal to 4, or r must be 2, which is b. I feel like I went through that very quickly and not necessarily in order. Is anyone confused about question 18? MC Ryan, do you want to ask a question?
The explanation was confusing for me.
Okay. Kyle, do you have a question? Okay, it looks like enough people want me to explain it again. So, I'm going to erase everything that's not red. In order to solve this equation, or this question, y is 2r squared. Yeah, we're going to need some formulas. Okay, let's erase this and write down some formulas. So, if you have any annotations on the screen, can you please erase them? I'm sorry, I'll slow down this time. So, we have area of a square. We're going to need this formula. Let's say we have the area of, or we have a square with side length s and diagonal d. Then the area of the square is equal to s squared, but it's also equal to d squared over 2. This is a formula you get for free for now. Is this question complicated to solve? It's a little bit of algebra for sure, and you have to know some
Like the area
formulas.
square is the oh, okay. Now I understand.
Okay. And if we have a circle with radius capital R, then Archimedes told us that the area of the circle is r squared pi. So we get both these for free. We're just allowed to use them. There's a reason why it's true that you can square the diagonal of a square and then divide by 2 and you'll get the area of a square. There's a lot of different ways to prove it. We're just going to use that formula for free for now. So let's talk about what is the area over here. I'm going to shade it in orange. What is this area? So orange is equal to circle minus square. So that, more questions? Do you want to just say it out loud? If it's a question? Or type it, you can. I'll keep writing, but go ahead and type it if you want. So the area of the circle is going to be the radius of the small circle. So the small circle has a radius of 1. And then it's times pi. So that's just equal to pi. And then the area of the square, is going to be 2 squared because this is too long. So minus 2 squared over 2. We have to divide it by 2. How do you find the length of one side of the square? The magical thing is we don't have to. We don't have to worry about that. So, yeah, we could. That's a good question for another time. We just don't have time. I'm using a strategy that doesn't need it. So, we have pi minus 2 for the orange area. And they're telling us that this orange area over here is actually the same. And all they tell us about this shape, this configuration, is that it has a big radius, r. So we have big radius r. And that is going to be equal to capital R squared times pi, so the area of the big circle, minus the area of the big square. This whole diagonal is 2r. So we're going to have 2r squared divided by 2. And then we're not taking all of these sectors now, or these caps. We're only taking one of them. So we have to divide by 4. But they told us that this thing was equal to this thing. I'm going to rewrite this so it's a little bit nicer. We have r squared pi minus 2r squared over 4. And then that's equal to pi minus 2. If we pull out an r squared and we multiply both sides by 4, we get r squared pi minus 2 is equal to 4 times pi minus 2. And we can cancel these out just by dividing by pi minus 2. So r squared is equal to 4. So then r must be 2. Some people think or claim to have a simpler method. I won't dispute with them about that, but I'm going to move on. All right, so two towns, A and B, are connected by a straight road, 15 miles long. Traveling from town A to town B, the speed limit changes every 5 miles, from 25 to 40 to 20 miles per hour. Two cars, one at town A and one at town B, start moving towards each other at the same time. They drive exactly the speed limit in each portion of the road. How far from town A in miles will the two cars meet? Okay, so one thing I want to point out before we do any math, before we think logically about anything, the answer choices tell us that the answer is going to be somewhere in here. Just by looking at the answers, we know it's got to be in there somewhere. So that is going to allow us to make some simplifying assumptions in a couple of minutes. But one thing that we will need, one tool that we need for this problem is what I call the dirt equation. D equals RT, the dirt equation. And what this means is that distance is equal to rate times time. Let me capitalize that. Times time. So this is the key tool that we're going to use over and over again. We want to know when they meet up, when they pass by each other, how far away from A will they be at that point? So how long does it take A to go 5 miles if A is going 25 miles per hour? So 5 is equal to 25 times T. I'm going to use lowercase for T. And this is in hours. That tells us that T is equal to 1/5 of an hour. Or T is equal to 12 minutes. Okay, so 12 minutes, A is driver 1 is here. Okay, 12 minutes. How long does it take driver 2 to go 5 miles at 20 miles per hour? Did someone raise their hand? Do they have a question? You can type it in chat or you can talk out loud, but otherwise I'm going to assume that was just an accident. Oh. Oh, someone is offering us an answer. I see. So how long does it take us to go 5 miles at 20 miles per hour? Well, again, we have 5 is equal to 20t, or t is equal to 1/4 hours, which is equal to 15 minutes. Okay? So by that point, when driver 2 is here, driver 1 has been driving for 40 miles per hour for 3 minutes. Okay? How 40 miles per hour for 1 mile, how many miles per minute are they going? So that's 1 is equal to 40t. So t is equal to 1/40 of an hour. 1/40th of an hour is a minute and a half. Yeah. So, wait, maybe that's not the correct calculation. Sorry, I've been doing math all day, even before I got here. So they go for 3 minutes at 40 miles per hour. How long do they go? How far do they go in 1 minute? Okay, so in 1 minute they go 1 mile equals 40 miles per hour time oh, never mind. I want distance is equal to 40 times 1/60th of an hour. So the distance is equal to 2/3 of a mile. So after 3 minutes, pardon me, that after 3 minutes, the first driver has gone 2 miles. Okay, so they're at the 7-mile mark and they are at the 10-mile mark. All right. Now they're going at the same speed. They're going to meet up in the midway point at 8.5 miles, which is D. Sorry, I got lost there for a second. There any questions about that one? 2 miles in 3 minutes, yeah. Sorry, that took me a minute. I was plugging into the equation wrong. Any questions before I move on? All right. So I have to say, these next few, they're a little bit difficult. This one, I am going to use an advanced trick. You can definitely like estimate the correct answer, especially if you have a calculator, but I'm going to use a trick that's a little advanced. All right, so let's first write down the amounts of cheese that they eat. So I'm going to have S, D, and R. Okay, so first S eats 1/2 of the cheese. Then D eats 1/4 of the cheese because it's 1/2 of 1/2 of what's left. And then Rajiv eats 1/8 of the cheese because it's 1/2 of 1/2 of 1/2 of what's left. Okay, then Sharika eats 1/16. Dev eats 1/32. Rajiv eats 1/64. Okay, I'm just going to go a little bit more and then I'll write ... dots. But there's some sort of pattern happening here. Okay, and then Sarika is going to eat 1/128 because we're just dividing by half again. Then 1/256. Then 1/512. And so on. Where the 3 dots mean that there's some sort of pattern. Right? Let's factor out. Yeah, okay. Thank you, Tyler. So the denominators are getting multiplied by 8 each time. That's exactly right. So the first one, I'm gonna, unfortunately, I think I'm gonna have to zoom out and write on the margins and zoom. So we have S equals, I'm gonna factor out a 1/2. 1/2 times 1 plus 1/8 plus 1/64 plus forever. All right. So how do we find out this infinite sum? Is infinite sum. Does it even make sense to talk about an infinite sum? In this case, it does. And we can actually find out what number it is, but we have to be a little bit sneaky. The first thing I'm going to do is I'm just going to focus on what's inside the parentheses. So I'm going to call S 1 plus 1/8 plus 1/64 plus ... And I want to see if anyone knows the trick or can suggest it before I... Some people are saying the right answer, but they're not saying how we find this infinite sum. I'm confident many people got the right answer just by guessing, or not guessing, but estimating. I want to find the exact answer. So, I want to get rid of the infinite part somehow. That part is standing in our way. This thing right here. We don't want to simplify because the denominator is going to keep getting bigger, so that numerator is going to get super ugly. So here's what we're going to do. If we multiply S by 1/8, all it does is shift over this infinite sum by 1. It's almost the same thing. It's just everything has gotten shifted over by 1. So what happens if we subtract these two things? Then we get S minus 1/8 of S is equal to 1. Or the sum of the blocks of cheese that Sarika ate is 7/8 times this sum. I guess we're gonna have to multiply by 1/2 at the end. So this is regular Sarika, and then this is fancy S. So it's equal to 1. Or big fancy S is 7/8. So Sarika is 1/2, or sorry, 8/7 of 8/7, just 4/7. And that's the exact answer if they kept eating forever. Eventually they stop when there's not enough cheese left. But that's one way to do it. It's a little bit of an overpowered method because we're eliminating an infinite sum by doing a little trick. But it's really powerful. This is actually one of the most powerful tricks in algebra. I need to
But
cough
if
for a
they eat
moment.
one and what 512th of like, that's basically a crumb.
Yeah, at a certain point, you can't split it up anymore, and so the person just eats the last one. And that's why they, instead of saying exactly how much, they say about how much. But in math, we can eat an infinite amount of infinitely small slices of cheese, and it's important to know how to do that. So that's why I showed us this trick. Any questions about this before I move on? Because I know this is probably most people's first time seeing that trick.
I'm
I don't-
s-
Go
I'm
ahead, Kyle.
trying to picture that right now.
Wait, yeah, please raise your hand if you wanna share something. Go ahead, Kyle. Why does removing the 1/8? Okay, so do you agree that when we multiply s by 1/8, it shifts everything over by 1? Okay. Now what happens when we subtract? You can just estimate, Luke. I'm just introducing a powerful trick because it helps in problems where you can't estimate. What happens when we subtract? We do 1 minus 0 plus 1/8 minus 1/8 plus 1 over 64 minus 1 over 64. And so all of these are canceling out. The only thing that's left over is the 1. Does that make sense? It's a very sneaky trick. It's like the multiplication version of Gauss's trick. I don't know how anyone ever came up with this. But anyway, it's a very powerful trick too. Again, it's one of the most powerful. I actually do use it in my college classes all the time. Serena, do you have a question?
Yeah, if you're subtracting 1/8 of s to the original s, I don't understand how you subtract 1/8 from 1/8 and 1/64 from 1/64, because wouldn't then you would just be subtracting s instead of 1/8 of s?
But there's no 1 here because we've shifted, multiplying by 1/8 has shifted everything over by 1. There's nothing to move into where 1 used to be, so now there's just a 0 there.
Oh, I understand now.
Awesome. Evan, good question. The name of this method is called geometric series. Sorry, I'll write that over here. So it's where I'm just going to write down the formula. If we have some number a plus a times g plus forever, right? A times g forever. So I guess the next one I should write down a couple. Plus a times g squared plus a times g cubed and so on. If you use a little bit of algebra, so again, let's call this fancy S. After a little bit of algebra, it turns out that the answer is a times a over 1 minus g. And g has to be, the absolute value of g has to be less than 1 because we're not allowed to divide by 0. And it doesn't really make sense otherwise because we're adding up bigger and bigger numbers if g is more than 1. But if g is less than 1, then we're adding up smaller and smaller numbers. So the infinite sum makes sense. That is very fast. I'm only saying this quickly because someone asked me to. In the class, we would normally spend a whole day or maybe even several weeks talking about this. So, any other questions before I erase the Zoom and move on? Hurry up. Okay, we have 11 minutes. We have 11 minutes. Apologize for not being able to go over the earlier questions again. I think there will be a recording of this as well. And I don't mind going a little bit late, but I won't hold anyone else to that. So the Königsberg School has assigned grades 1 through 7 to pods A through G, 1 grade per pod. Some of the pods are connected by walkways as shown in the figure below. The school noticed that each pair of connected pods has been assigned grades differing by 2 or more grade levels. For example, grades 1 and 2 will not be in pods directly connected by a walkway. What is the sum of the grade levels assigned in pods C, E, and F. Okay, this is a great one. This is directly has to do with something that I talked about recently. Let's talk about C, E, and F. Okay, so what we have here is something called a mathematical graph or a network, and it consists of nodes and connections. And each node in this graph, so like A, B, C, D, E, F, G, those are all nodes in this graph or this network. They have a number called a degree. And the degree is the number of connections coming out of them. So the degree of A is 4. The degree of B is 3. The degree of C is 5. The degree of D is 2. The degree of E is 3. The degree of F is also 5. And the degree of G is 2. So again, the degree is the number of connections that the node has to other nodes in the network. Two of our things that we are worried about, C and F, have the highest degrees in the network. That's 5. Okay, so there are 5 numbers that they have to be next to in this network. Since we're only allowed to choose the numbers 1 through 7, one of these has to be 1 and one of them has to be 7. It turns out it doesn't really matter which one is which, so I'm going to say that this is 1 and this is 7. Okay, so let me erase the degrees. We know that 1 has to go there and 7 has to go there. Now, G is next to 7, and it is far away from 1. So the 2 can't go here. This can't be the 2, and the 2 can't go here. So and it can't be in these other 2. The only one that the 2 can be in is over here in G. All right, so we have a 2 here. The last 2 questions take 30 seconds each. Oh, I guess you don't need my help going through them then. So over here, this one has to be 6. And C, E, and F. So this is next to, this has to be different. This can't be 3. It can't be 6. So let's say this is 5. I'll make this 4 and this 3. That looks good to me. So we're trying to add up these 3. That adds up to, 11. That's not an answer. 4 and 5 can't be next to each other. Sorry. Make this 3 and this 4. And that adds up to 12, which is A. All right. So, a classroom has a row of 35 coat hooks. Paulina likes the coats to be equally spaced so that there is the same number of empty hooks before the first coat and after the last coat. And between every coat and the next one, suppose there is at least one coat and at least one empty hook. How many different numbers can satisfy this pattern? Okay, so let's say there are n coats. So that means that there are n plus 1 spaces, because we have one on the outside and then these 3 here. So this is with 2 coats. 3 spaces. Coats. Let me spell coats correctly. Sorry. Not cats. 2 coats. 3 spaces. And there is 35 minus n empty hooks. Okay, so since the number of spaces needs to divide the number of hooks, we have n plus 1 is a divisor of n minus 1. Okay, so we only need to check to roughly the square root of this, and it's going to give us, sorry, that's not right. We have to check up to half, not the square root, up to half. So I would just brute force check it at this point. So I'm going to write down the answers that do work. So n could be equal to 1, 2, 3, 5, 8, 11, 17. For the sake of time, I'm going to let you guys check that these are all of the values of n that will work. You only have to check from 1 to 18. There are 7 of them. All right, so problem 23. How many 4-digit numbers have all three of the following properties? The tens digit and the ones digit are both 9. The number is 1 less than a perfect square, and the number is the product of exactly two prime numbers. So if the number is 1 less than a perfect square, we can write it something like this. A squared minus 1. Some number a, whatever it is, minus 1. Since the tens digit and the ones digit are both 9, this is equal to something blank blank 99. So what that means is we need a multiple of 10 for our square. So a could equal 40, 50, 60, 70, 80, 90, but only these, because if a equals 30, then 30 squared is 900. That's not a 4-digit number. And if a is equal to 100, then 100 squared is equal to 10,000. That's also not a 4-digit number. So we only have to check these 5. Now I'm going to use one more thing. There's one more thing that we haven't used so far, and that is that the number is a product of exactly two prime numbers. There is a certain trick that we can use without having to square these things and then subtract 1 and then try to factor them. Whenever we see an expression like this, we're allowed to use a certain formula. For the sake of time, I'm just going to write it down. It's a very powerful formula, though, and I'll tell you the name. It's called the difference of squares formula. Okay, so the difference of squares formula says that anything that looks like a squared minus 1 is actually the same as a plus 1 times a minus 1. This seems like an incredible fact. If you're just looking at it for the first time, that seems super convenient. Because now what we can say is, okay, if a equals 40, then we get 39 times 41 for a squared minus 1, but 39 is not prime. All right, if a equals 50, then we get 49 and 51 for a squared minus 1, but again, 49 is not prime. If a equals 60, then we get 59 and 61. Both of these are prime. So this one works. Here's an example of a working number. I'm going to go back up to the top. I'll do it in red. So if a equals 70, then we get 69 and 71. This is actually equal to 3 times 23. And if a is equal to 80, then we get 79, and 81. This one is not a prime number. And if a is equal to 90, then we have 89 and 91. Now, this one is sneaky. How do I know that the hundreds is a 0? Because it has to end in 99. It has to end in 99. This one's sneaky because 91 is actually not prime. A lot of people don't expect this. 91 is equal to 7 times 13. So there's only one number that has this property. It's 60 squared minus 1, whatever that looks like. We don't have to compute it right now. All right. I think that 25 is more interesting. So for the sake of time, just so that everyone who planned to be here for 90 seconds or 90 minutes can see 24 problems, I'm going to do this one, and then I'll go back to 24. All right, so Michaela finds all the possible ways to draw a path in a 5x5 diamond-shaped grid. Each path starts at the bottom of the grid and ends at the top, always moving 1 unit northeast or northwest. She computes the area of the region between each path and the right side of the grid. The 2 examples are shown in the figures below. What is the sum of the areas determined by all possible paths? Okay, so this one is really nice. There's a lot of things that you can notice here that'll make it simple. Let's say I have a path like this, okay, and it has this area. If we mirror image the path, then we get something like this. Am I doing that correctly? No, I am not. If we mirror image the path, and I'm going to use a darker blue, then we get something like this. Goes 3, and then it goes 2, and then it goes 2 again, and 1. Oh, I guess I was doing it right the first time. And the area of this path, if we reverse it, it just flips around back to the original spot. It's equal to the left half. So every path can be paired up with another path, so that when we add their areas, I'm going to write this down in English. Every path can be paired with another path and exactly 1, so that their combined areas are 25 squared. So it's 25. So all we need to do is find the number of paths, divide it by 2, and multiply it by 25. So paths divided by 2, all times 25. All right, so that makes this problem really simple if we can just count the number of paths, but you might be saying to me, Mr. Corbin, how the heck are we going to count all the paths in this grid? There is a lot of them. There's over 250 of them, in fact. But there is a method which will let us compute that. If you've been in my class before, you've seen this method many times. It is a very powerful method on the AMC8. If you know this method, you can solve quite a bit of problems that otherwise are impossible. So each path starts at the bottom and goes up to the top. So here's what we're going to do. We're going to imagine a source of water pouring to the bottom of the grid. Okay, so it flows a number 1 into the bottom. And this number 1 is going to spread out upwards, right and left. But every time we run into a spot, a vertex, where multiple numbers are coming in, we're just going to add up the numbers. So this one has 2 1s coming in, so it becomes a 1. This one has a 1 coming in. This one has a 1 coming in, but this one has a 1 and a 2, so we get a 3 here. This one has a 1 and a 2, so this gets a 3 here, and this just has a 1. Okay, and then we get a 1 here, and this has a 1 and a 3 flowing in, so that is a 4. This has a 3 and a 3 flowing in, so this is a 6. This is a 3 and a 1 flowing in, so this is a 4. And this just has a single 1 flowing in. This has a 1 flowing in. This has a 5. This has a 6 and a 4, which is 10. This has a 4 and a 6, which is 10. This has a 4 and a 1, which is 5. And this has a single 1. Okay, now the rows are getting smaller. This one has a 5 and a 1, which is 6. This one has a 5 and a 10, which is 15. This one has a 10 and a 10, which is 20. This one has a 10 and a 5, which is 15. This one has a 1 and a 6, or 1 and a 5, which is 6. At this point, you might be noticing a lot of patterns. There's a lot more going on underneath the surface here. Not all of it is relevant to this problem, but I encourage you to remember what's going on here because you'll probably see it again. 15 plus 6 is 21, and then we have a 35, and then a 35, and then a 21. And then up here, we have a 35 plus 21. The numbers are getting kind of big. We have a 56, and then a 35 plus 35 is 70, and then 21 plus 35 again is 56. Let me just finish this, and then I will answer questions. We're going over time a little bit. And then we have 126 and 126. If we add those up, we get 252. It's quite a bit, but that is the number of paths. It's like Pascal's triangle. Great observation. So we have 252 divided by 2 times 25. That is equal to 126 times 25, which is B. All right. I know that was pretty fast, and I used a technique that I didn't explain why it worked. With that being said, any questions? Any questions? I don't want to hear other ways, but Joshua, what's your question? We will go back to 24. Annie, do you have a question? People aren't allowed to unmute. Can you type the question to me?
Okay, you can unmute now.
Is there another like faster way to do this?
This was the fastest way. I mean, look at that
Oh,
number.
meaning there's nothing faster than this.
Nothing that I know.
Oh, so this is like the fastest way.
Pretty much. Any other
Oh.
questions? Why 25? Because if we add up this area plus this area, it's 5 by 5.
Can you use this pattern for other questions like this?
Lots of other questions like this. This is a very powerful technique. This is called the water pipes technique. What I did right here. It is used on a lot of problems on this.
Oh, I remember that.
Why is it called water pipes if it flows up? Good question. Usually we don't care about the orientation of the flow. We just care that there's a start and a stop. Yes, we can go back to question 24. I just wanted to address this one because technically class has been over for 6 minutes. I'm going to keep going so that everyone gets a chance to see all of them. But I just wanted to make sure that if someone had to leave after 90 minutes, they got to see what I consider the most interesting questions. Tyler, was I able to answer your question about why it's 25? I don't know if that person is still in the meeting.
Can we go back to 24?
Yes. Okay. So, in trapezoid ABCD, angles B and C measure 60 degrees, and AB equals DC. The side lengths are all positive integers, and the perimeter of ABCD is 30 units. How many non-congruent trapezoids satisfy these equations? All right, so let's call this X. I'm going to drop down these heights. Okay, so this is X. This is, let's call it Y, and this is Y. What is the method that I use to eliminate the infinite called? I'll tell you about that after this. So, now if we have a 60-degree angle in a right triangle, then the other one is 30. This is actually half of an equilateral triangle. So if this is y and this is y, then this is 2y, and this is 2y. So this is 2y, and this is 2y. So we have altogether the perimeter of this thing is going to be 2x plus 6y is equal to 30. All three of these numbers are even, so we could rewrite this as x plus 3y is equal to 15. How many pairs of numbers are there that satisfy this possibility? We could have x is equal to 3, x is equal to 6, x is equal to 9, and x is equal to 12. That would mean that y is equal to 4, or y is equal to 3, or y is equal to 2, or y is equal to 1. Why is it 2y on the hypotenuse? Because this is half of the base of an equilateral triangle. So the whole sides of the equilateral triangle is 2y. Annie, do you have a question?
What does non-congruent mean?
Non-congruent means they're not the same size. X and Y cannot, either one of them cannot be 0 because then it would not be trapezoid. Serena, do you have a question?
Why can x only be multiples of 3?
15 is a multiple of 3, right?
Yeah.
And 3y is a multiple of 3?
Yeah.
And if I add something that's not a multiple of 3 to a multiple of 3, am I going to get a multiple of 3?
Oh, I understand now. You're not going to get a multiple of 3 if you...
Great question. I'm here all night, folks. Any other questions?
Nope.
Technically, we have been here for longer than you were required to go. You're definitely dismissed if you would like. I'll stick around for a couple more minutes if any parents have questions as well.
I need to go to bed.
It was great. It was great meeting you all. Oh, yes, the method that you're free to go. So the method that I was using earlier to eliminate the infinite part is called geometric series.
Okay, thank you. I think I can just search it up.
Yep.
Wait, actually, I already know what geometric series are.
Well, yes, but someone else was asking me about it.
Okay, bye.
Later.
All right, I think we all learned like quite a few powerful tricks tonight. It's really helpful and very eye-opening to me as well. 各位家长，如果你们有任何问题的话，如果对 Corbin 老师的 AMC8 的课程，然后他也辅导 AMC10 Amy 的数学竞赛，那如果对他的任何课程有任何问题，那我下星期的时候会有 Corbin 老师的新课会开课，也是同一时间，就是周五的晚上8点半。东部时间8点半，就是西部时间的晚上5点半到7点钟。All right, that's it for today, and good night, everyone.
Thank you. Bye.
It was nice meeting everyone. Good night.
Bye. Thank you.
好，有什么问题的话，我们可以在群里头继续沟通。好，那就感谢大家参加今天的这个公开课，那我们回头见，拜拜。